Imagine if we could predict financial fraud before it happens, detect cyber attacks in real time, or even identify early signs of disease long before symptoms appear. That's exactly what anomaly detection is doing right now. It's one of the most powerful AI techniques shaping industries worldwide. And here's the thing, anomalies matter. They're the rare events, the hidden outliers, the small but critical signals that can mean the difference between catching a security breach or suffering a massive data leak. The problem? They're hard to find. Traditional methods miss them. That's where AI and machine learning come in, revolutionizing the way we detect these rare but impactful occurrences. In this deep dive, we're going to break it all down: how anomaly detection works, the different techniques behind it, the biggest challenges, and the real-world applications that are transforming cybersecurity, finance, healthcare, and more. By the end of this, you won't just understand anomaly detection. You'll see it everywhere and understand why it's one of the hottest topics in AI. So stick around, hit that subscribe button, and let's jump into the foundations of anomaly detection. Imagine you're a bank analyzing millions of transactions per day. Among all the regular deposits, transfers, and payments, there's one unusual transaction: a small, almost invisible withdrawal from an account. No red flags at first glance. But over time, that same pattern repeats across thousands of accounts. Suddenly, you realize this isn't random, it's fraud. That's the power of anomaly detection, finding the one in a million event that matters. It's not just about spotting rare things, it's about detecting meaningful deviations that signal something important. Anomaly detection, also called outlier detection, is a technique that identifies rare events or observations that deviate significantly from the norm. In some cases, these anomalies signal threats, like fraud, cyber attacks, or equipment failures. In others, they reveal new opportunities, like identifying breakthrough trends in financial markets or discovering early warning signs in medical research. And here's the challenge: anomalies don't always look the same. Some are clear and obvious, a huge spike in website traffic after a viral post. Others are subtle, like a patient's heart rate fluctuating slightly before a major health event. This means that traditional rule-based detection methods often fail, which is why we turn to AI and machine learning to find patterns that humans simply can't. The key takeaway? Anomalies aren't just noise, they tell us a story. The challenge is learning how to listen, and that's what we're about to do. Because not all anomalies are created equal. There are different types of anomalies, and understanding them is the first step in building better detection systems. So, up next, the three types of anomalies: point, contextual, and collective. Let's go. Imagine you're monitoring a city's traffic flow. Most cars follow predictable routes: morning rush hour, lunchtime lulls, evening commutes. But then you notice something strange: a single car driving in circles for hours. That's weird. Then you spot another anomaly, a traffic jam in the middle of the night with no explanation. And then, even more unsettling, every car at a certain intersection is stopping for no reason. These are all different kinds of anomalies, and in data science, we classify them into three main types: point anomalies, contextual anomalies, and collective anomalies. The simplest form is the point anomaly. This is when a single data point sticks out like a sore thumb. Imagine you're analyzing credit card transactions, and someone who normally spends $50 per week suddenly drops $50,000 in a single purchase. That's an anomaly. It's rare, unexpected, and might indicate fraud. These are the easiest to detect, but in many cases, real-world anomalies are more complex. That brings us to contextual anomalies. These are values that seem normal in general, but when viewed in context, they don't make sense. Think of temperature data. 30-degree T's is perfectly normal in winter, but would be highly unusual in the middle of summer. Context matters. In cybersecurity, a user logging in at 9 a.m. is fine. But if the same user logs in from another country 5 minutes later, that's suspicious. Contextual anomalies help us detect subtle, sophisticated threats that simple detection systems might miss. And finally, we have collective anomalies. These happen when a group of data points together behave unusually, even if each individual point seems fine. Imagine a sudden surge of traffic to a website, all from a single IP range. By itself, one visit isn't strange, but hundreds of visits from the same source could indicate a cyber attack. Or in healthcare, a hospital might notice a small increase in patients with a rare symptom. Alone, these cases might seem random, but together they could signal the early signs of an epidemic. Understanding the different types of anomalies is critical because it helps us design better detection systems. Some problems require spotting one-off spikes, while others depend on recognizing patterns over time. And this is why anomaly detection is such a fascinating challenge, because the right anomaly at the right moment can change everything. But here's the real question. How do we actually detect these anomalies? What's the process behind finding them? That's exactly what we're about to break down next. The anomaly detection pipeline, how machines learn to spot the unexpected. Let's dive in. Imagine you're a security analyst at a massive online retailer. One day you notice a customer has placed 100 separate orders, all for the same low-value item, in under a minute. Is it fraud, a bot attack, a glitch? Before you can act, you need to be sure. But how? That's where the anomaly detection process comes in, a structured step-by-step pipeline that helps us detect, analyze, and act on anomalies effectively. Because in industries like finance, cybersecurity, and healthcare, false alarms can cost millions, but missing real threats can cost even more. The first step is data collection. Before we can find anomalies, we need data. Lots of it, whether it's network traffic, financial transactions, medical records, or sensor readings. The quality and quantity of our data define how well our models will perform. Imagine trying to detect fraud with only a handful of transactions. You'd miss most anomalies. The more diverse and representative the data, the better. Next, we move to data pre-processing. Raw data is often messy, incomplete, and noisy. There might be missing values, duplicate records, or inconsistent formats. If we don't clean this up first, our anomaly detection system might mistake bad data for real anomalies. Think of this step as preparing a detective's evidence board. Every detail needs to be clear, organized, and reliable before drawing any conclusions. Now comes the heart of anomaly detection, model selection. This is where we decide how we're going to find the anomalies. Should we use statistical methods, machine learning algorithms, or deep learning models? If we have labeled data where past anomalies are already identified, we can train a supervised learning model to recognize similar patterns. If we don't, we rely on unsupervised learning, which detects anomalies based on deviations from normal patterns. The choice of model depends on the complexity of the data and the problem we're solving. Once we have a model, it's time for evaluation. This is where we test how well the model detects anomalies using metrics like precision, recall, and F1 score. A good model should catch real anomalies while avoiding false alarms. If it flags too many normal events as anomalies, it becomes useless. If it misses real threats, it's even worse. Tuning the model and refining its parameters is a continuous process, because anomaly detection is never one and done. And finally, deployment and monitoring. Once the model is live, it continuously scans new data for anomalies in real time. But here's the challenge. Data changes over time. A model trained on last year's data might fail to detect new types of fraud or cyber attacks that emerge today. That's why ongoing monitoring and retraining are critical. AI-powered anomaly detection systems need to evolve just like threats do. From collecting data to cleaning it, choosing the right model, evaluating its performance, and keeping it up to date, every step in this pipeline is crucial. Because anomaly detection isn't just about spotting the unusual, it's about understanding the story behind it. But the choice of model is one of the biggest factors in how well anomaly detection works. And that's exactly what we're diving into next. Supervised versus unsupervised anomaly detection. Which one works best and when? Let's break it down. Imagine you're a detective trying to catch criminals in a city. In one case, you have mugshots and records of known criminals, so you can quickly identify new offenders based on past data. But in another case, you have no prior records, and you have to rely on instincts spotting suspicious behavior, tracking patterns, and making educated guesses. That's exactly the difference between supervised and unsupervised anomaly detection. Two different approaches, each with its strengths and weaknesses, but both crucial for finding anomalies in complex data. Let's start with supervised anomaly detection. This method relies on labeled datasets, where past anomalies have already been identified and tagged. The model learns from this historical data and recognizes similar patterns in new data. Think of a fraud detection system in a bank. If a bank has thousands of examples of fraudulent transactions, it can train a model to recognize the exact patterns that indicate fraud. Supervised methods tend to be highly accurate, but they come with a huge limitation. They require labeled data. And in anomaly detection, labeled data is often scarce, expensive, or even non-existent. In cybersecurity, for example, hackers constantly invent new attack techniques, so a model trained on old threats might completely miss new ones. That's where unsupervised learning comes in. Unsupervised anomaly detection is like a detective working with no prior records. Instead of recognizing known criminals, it identifies any unusual behavior that deviates from the norm. This is perfect for situations where anomalies are rare or constantly evolving, like network security, where attackers use new tactics every day. The biggest advantage: no need for labeled data. The model finds anomalies by learning what normal looks like and flagging anything that stands out. Imagine a factory monitoring thousands of sensors in real time. If one machine suddenly starts behaving abnormally, the AI doesn't need prior examples to detect it. It just knows that something is off. But there's a downside. Unsupervised models can sometimes overreact. They might flag rare but normal events as anomalies, leading to false alarms. In a hospital, an unsupervised system might alert doctors about a harmless but unusual heartbeat pattern, wasting valuable time. So which one is better? It depends. If labeled data is available and anomalies follow predictable patterns, supervised learning is the best choice. If anomalies are unpredictable, rare, or evolving, unsupervised learning is more effective. And in many real-world applications, the best approach is a hybrid of both, combining the accuracy of supervised learning with the adaptability of unsupervised methods. But regardless of the approach, anomaly detection is only as good as the model behind it. And that brings us to the real magic, the algorithms that power anomaly detection. Let's explore them next. All right, now we're getting to the real brains behind anomaly detection, the algorithms that power it. Because whether we use supervised or unsupervised learning, the effectiveness of anomaly detection depends entirely on the model we choose. Think of anomaly detection like finding a needle in a haystack. Some algorithms are like magnets pulling out anomalies efficiently. Others act like scanners, analyzing patterns to detect what doesn't belong. Each has its strengths, and the choice of algorithm depends on the complexity of the data, the type of anomalies we're looking for, and how fast we need results. One of the most widely used algorithms is isolation forest. Unlike traditional models that try to define normal, isolation forest does something unique. It actively isolates anomalies. It works by randomly selecting features and splitting the data over multiple iterations. Since anomalies are rare and different, they get isolated faster than normal points. This makes isolation forest fast, scalable, and highly effective, especially for large datasets like financial transactions or network logs. Another powerful method is k-nearest neighbors, KNN. This algorithm looks at the distance between data points. If something is much farther away from its closest neighbors, it's flagged as an anomaly. KNN is great for detecting outliers in structured data, like spotting an unusually high medical bill compared to similar patients, but it struggles with high-dimensional data where distance measurements become less reliable. For more complex and flexible anomaly detection, we use autoencoders. These are deep learning models that work by compressing data into a lower dimensional form and then reconstructing it. If an input is too different from what the model has learned, the reconstruction error is high, signaling an anomaly. Autoencoders shine in detecting subtle, non-obvious anomalies, like defects in images or abnormal heart rhythms in ECG signals. Another go-to technique is support vector machines, SVM. This algorithm defines a boundary that separates normal data from anomalies. Anything that falls outside this boundary is flagged as an outlier. SVMs work well for binary classification problems like identifying fraudulent versus normal transactions, but they struggle with large-scale real-time detection. And then we have local outlier factor, LOF. Unlike other algorithms that look at global patterns, LOF focuses on local density. It checks how different a point is compared to its nearest neighbors. This makes it especially good for detecting contextual anomalies, like unexpected shifts in stock market trends or unusual temperature fluctuations in industrial sensors. Each of these algorithms has its own strengths and weaknesses, and the best choice depends on the problem at hand. Need speed and scalability? Isolation forest. Looking for anomalies in structured data? KNN or LOF, working with deep, complex patterns? Autoencoders. Need a strict decision boundary? SVM. But here's the challenge. Real-world data is messy, and no algorithm is perfect. In practice, we often combine multiple approaches to improve accuracy and reduce false positives. But even with the best algorithms, anomaly detection isn't easy because real-world data comes with major challenges, and if we don't handle them right, even the smartest models can fail. And that's exactly what we're tackling next, the biggest challenges in anomaly detection, why it's harder than it looks. Let's break it down. All right, so we've got powerful algorithms, massive datasets, and AI models working to detect anomalies. But here's the truth. Anomaly detection is way harder than it looks. Think about it. Anomalies are rare, unpredictable, and constantly changing. If they were easy to find, we wouldn't need AI in the first place. But in reality, there are 4 major challenges that make anomaly detection one of the toughest problems in machine learning. The first big challenge, noise and variability. Not every unusual event is an anomaly. Real-world data is messy, filled with random fluctuations, missing values, and natural variations that could be mistaken for anomalies. Imagine an e-commerce site that suddenly sees a spike in traffic. Is it a DDoS attack or just a flash sale gone viral? If an AI model can't distinguish between meaningful anomalies and random noise, it will either miss real threats or flood you with false alarms. Next up, high dimensionality. Modern datasets aren't just big, they're complex. Financial transactions, network security logs, medical imaging, they all have hundreds or thousands of features. But here's the problem. As the number of dimensions increases, distance-based methods, like KNN, become less reliable because everything starts looking equally far apart. This is known as the curse of dimensionality, and it makes anomaly detection significantly harder in high-dimensional spaces. And then there's the biggest challenge of all, imbalanced data. Anomalies are rare by definition. In fraud detection, less than 1% of transactions might be fraudulent. In medical diagnosis, diseases could be present in less than 0.1% of cases. If you train an AI model on this kind of data, it might learn to simply ignore anomalies altogether because they're so uncommon. Imagine a model that predicts normal 99.9% of the time. It looks accurate, but in reality, it's useless because it fails to catch the rare events that actually matter. This imbalance makes it difficult for machine learning models to learn meaningful patterns for detecting anomalies. And finally, evolving data patterns. Anomalies don't stay the same forever. In cybersecurity, hackers constantly change tactics to bypass detection. In finance, market trends shift, making old fraud detection patterns outdated. Even in healthcare, disease symptoms evolve, requiring continuous model updates. If an anomaly detection system isn't regularly updated, it becomes obsolete, missing new types of threats and generating too many false positives on normal but changing patterns. So, what's the solution? To handle noise, we use data preprocessing techniques, removing inconsistencies, normalizing values, and filtering out random fluctuations. For high-dimensional data, we use techniques like dimensionality reduction, PCA, TSNE, or models that can automatically learn meaningful representations like deep learning autoencoders. To fight imbalanced data, we use techniques like oversampling, semote, undersampling, or anomaly-aware loss functions that prevent models from simply ignoring rare events. And to tackle evolving patterns, we implement continuous learning, where AI models retrain on the latest data and adapt to new anomalies in real time. The truth is, anomaly detection is a moving target. It's not about finding the right answer once, but building systems that keep learning, adapting, and improving over time. And nowhere is this challenge more critical than in the industries where anomalies cost billions of dollars. Up next, we'll explore one of the biggest real-world applications, anomaly detection in finance, how banks and businesses use AI to prevent fraud. Let's dive in. Imagine waking up one morning, checking your bank account, and seeing a $10,000 charge for something you never bought. Your heart stops. Fraud. But here's the thing. Your bank already knew. Before you even saw the transaction, an AI-powered anomaly detection system had flagged it as suspicious, frozen your account, and sent you an alert. That's the power of anomaly detection in finance. Financial systems process millions of transactions per second, and somewhere in that ocean of data, anomalies, fraudulent activities, money laundering, or hidden risks are waiting to be found. The problem? They don't look the same every time. Criminals constantly evolve, making fraud detection a never-ending arms race. One of the biggest areas where anomaly detection shines is fraud detection. AI models scan transaction patterns looking for subtle deviations that might indicate fraudulent behavior. If a customer usually spends small amounts locally but suddenly makes a huge international purchase, the system flags it instantly. Banks report that AI-powered fraud detection has reduced fraud losses by up to 50%, making it one of the most valuable defenses against cybercrime. Then there's risk management. Financial institutions are exposed to enormous risks, from market volatility to bad loans. By using anomaly detection, banks can monitor for unusual fluctuations in stock prices, credit defaults, or suspicious trading behaviors. Identifying these anomalies early allows firms to take proactive measures, potentially saving millions in losses. And let's not forget transaction monitoring. Regulatory compliance is a massive challenge for banks, requiring them to track and report suspicious activities like money laundering. AI-powered anomaly detection continuously scans transactions in real time, flagging unusual cash flows, hidden connections between accounts, and rapid, unexplained fund movements. Financial institutions using these systems have reported a 30% increase in detection rates of money laundering activities, strengthening compliance and security. But here's the challenge: false positives. If anomaly detection systems are too sensitive, they'll flag too many normal transactions as fraud, frustrating customers and causing unnecessary account freezes. If they're not sensitive enough, real fraud slips through. The key is finding the perfect balance, which is why banks use a mix of machine learning, deep learning, and rule-based models to fine-tune their detection systems. Finance is just one industry where anomaly detection is critical, but there's another where it's literally a matter of life and death. Up next, anomaly detection in healthcare, how AI is saving lives by detecting medical anomalies before it's too late. Let's go. Imagine a patient arrives at the hospital feeling fine, but their wearable device detects a subtle, unusual pattern in their heart rate. It's nothing obvious, something a doctor might not even notice. But an AI-powered anomaly detection system does. It flags the anomaly, alerts the medical team, and within hours, the patient is diagnosed with a life-threatening heart condition, just in time to prevent a heart attack. This isn't the future. It's happening right now. Anomaly detection in healthcare is revolutionizing the way we diagnose diseases, monitor patients, and prevent medical emergencies. The human body is full of complex, constantly changing data, heart rates, blood pressure, oxygen levels, and countless biological signals. AI-powered systems analyze these patterns in real time, spotting the hidden warning signs that even expert doctors might miss. Sensors continuously collect data from patients, tracking vitals, sleep patterns, glucose levels, and even neurological activity. If an anomaly appears, a sudden drop in oxygen levels, an irregular heartbeat, or a dangerous spike in blood sugar, the system immediately alerts doctors, allowing for life-saving intervention. Another major area is disease outbreak detection. AI is being used to analyze massive datasets of medical reports, hospital admissions, and even social media trends to detect the early signals of emerging diseases. For example, during the COVID-19 pandemic, anomaly detection helped identify outbreak clusters before traditional reporting systems, enabling governments and health agencies to respond faster and more effectively. And then there's medical imaging. Radiologists analyze thousands of X-rays, MRIs, and CT scans every day, but AI-powered anomaly detection systems are now assisting them by highlighting subtle abnormalities that could indicate tumors, fractures, or internal bleeding. In fact, studies show that deep learning models can detect certain types of cancer earlier than human doctors, improving survival rates and treatment outcomes. But here's the real challenge: false positives. If an AI system is too aggressive, it might flag normal variations as medical emergencies, leading to unnecessary stress, extra tests, and increased healthcare costs. If it's too lenient, it could miss real life-threatening anomalies. The balance between sensitivity and specificity is what makes AI-driven healthcare one of the most exciting but challenging frontiers in medical technology. And healthcare isn't the only industry where anomaly detection plays a critical role. There's another field where catching anomalies in real time is the only thing standing between security and disaster. Up next, anomaly detection in cybersecurity, how AI is fighting cyber threats before they strike. Let's dive in. Imagine you're the head of cybersecurity for a major company. Everything seems normal. Employees are logging in, emails are flowing, and transactions are being processed. But behind the scenes, something isn't right. A user account, which usually logs in once a day, has just attempted 50 logins in under a minute from 3 different locations. At first glance, it's just another login attempt, but your AI-powered anomaly detection system sees what humans don't. It recognizes the pattern is unusual, flags it as a potential cyber attack, and locks the account before any damage is done. That's the power of anomaly detection in cybersecurity, detecting threats before they become disasters. Traditional rule-based security systems ineffective against new threats. AI-driven anomaly detection is now the frontline defense against modern cyber attacks, monitoring networks in real time and spotting the smallest deviations that indicate a breach. One of the most critical areas where anomaly detection shines is intrusion detection. AI continuously scans network traffic, looking for unusual behavior, a sudden spike in data transfers, unauthorized access to sensitive files, or unexpected activity in restricted systems. If an employee account that has never accessed critical databases suddenly starts downloading gigabytes of data at 3 a.m., that's an anomaly, and likely an insider threat or a compromised account. Another major application is malware detection. Traditional antivirus software relies on predefined threat signatures, meaning it can only stop known malware. But AI-powered systems analyze behavior instead of signatures, detecting malware even if it's brand new. If a file suddenly starts modifying system processes in an unusual way, the system flags it as a potential threat before it spreads. And then there's fraud prevention. Cybercriminals use sophisticated phishing scams, fake transactions, and identity theft tactics to bypass security measures. AI-powered anomaly detection scans, login behaviors, transaction histories, and communication patterns to spot fraud attempts in real time. If a bank customer who usually logs in from the US suddenly tries to wire $50,000 from an IP address in Russia, the system automatically blocks the transaction and requests additional verification. But just like in finance and healthcare, cybersecurity faces challenges. False positives can overwhelm security teams with too many alerts, while false negatives could let a devastating attack slip through. That's why AI-driven cybersecurity systems use continuous learning to improve over time, becoming more accurate with every detection. And cybersecurity is just one piece of the puzzle. Anomaly detection isn't just about stopping fraud or hacking. It's also transforming how we manage complex industrial systems, preventing failures before they happen. Up next, anomaly detection in industrial systems. How AI is preventing disasters in factories, energy grids, and smart cities. Let's dive in. Imagine a power plant managing thousands of machines, each running 24/7 to supply electricity to millions of homes. Everything seems normal until one turbine starts vibrating slightly more than usual. It's not enough for human operators to notice, but an AI-powered anomaly detection system picks up the deviation. Within minutes, engineers are alerted. The machine is shut down for inspection, and a catastrophic failure is prevented. That's the power of anomaly detection in industrial systems, catching tiny, hidden warning signs before they turn into full-scale disasters. Factories, energy grids, transportation networks, and smart cities rely on complex, interconnected systems. When something fails, the consequences can be devastating. Damaged equipment, costly downtime, environmental hazards, and even human lives at risk. Anomaly detection helps prevent failures by monitoring massive amounts of sensor data in real time, identifying early warning signals, and triggering proactive maintenance. One of the biggest applications is predictive maintenance. Industrial equipment wears down over time, but instead of waiting for a breakdown, AI can predict exactly when a machine is likely to fail. By analyzing sensor readings like temperature, pressure, vibration, and voltage, anomaly detection models spot early signs of degradation, allowing companies to schedule maintenance before a failure occurs. This reduces downtime, lowers costs, and extends the lifespan of machinery. Another critical use case is fault detection in energy grids. Power plants and electrical grids operate under extreme conditions, and a single failure can cause cascading blackouts. AI-powered anomaly detection monitors voltage fluctuations, current surges, and power loads, identifying potential weak points before they fail. In fact, major energy providers are already using AI to prevent power outages, optimizing grid performance and protecting infrastructure from cyber threats. And then there's smart cities and infrastructure monitoring. Modern cities are filled with traffic sensors, water systems, and transportation networks that need constant monitoring. AI-driven anomaly detection helps prevent water leaks, detect faulty traffic signals, and optimize public transportation routes based on real-time data. In aviation, AI scans aircraft sensor data to identify engine irregularities, reducing the risk of failures mid-flight. But industrial anomaly detection isn't without challenges. Machines naturally exhibit small variations in performance, and distinguishing between normal wear and tear and true anomalies requires highly accurate models. False alarms can lead to unnecessary maintenance costs, while missing real anomalies can result in catastrophic failures. The solution? AI-powered self-learning systems that continuously improve their accuracy by adapting to changing conditions and evolving patterns. And while anomaly detection is making industries safer and more efficient, it's also driving innovation in cutting-edge AI research. Up next, the future of anomaly detection. What's next in AI and machine learning? Let's explore where this technology is headed. Let's pause for a moment and think about this. In today's hyper-connected world, where billions of data points are generated every second, the ability to act in real time isn't just a luxury, it's a necessity. This is where real-time anomaly detection comes into play. It's the cutting-edge technology that allows organizations to instantly identify unusual patterns and act on them, often preventing disasters before they even begin. Real-time anomaly detection enables us to spot and respond to unusual activity the moment it happens, whether it's detecting a fraudulent transaction, identifying a sudden spike in network traffic that indicates a cyber attack, or catching a critical health issue in a patient's vitals. This technology delivers instant insights and action. Here's why this matters. In industries like finance, healthcare, and cybersecurity, delays can mean millions in losses or even lives at stake. Traditional anomaly detection methods, while powerful, often analyze data in batches or after it's been stored. By then, the damage could already be done. Real-time systems, on the other hand, process streaming data on the fly, enabling responses in milliseconds. But how does it work? At its core, real-time anomaly detection relies on two primary techniques: streaming data processing and online learning. Streaming data processing is all about keeping up with the constant flow of information. Instead of waiting for a dataset to be completed, the system analyzes incoming data as it's generated, identifying patterns and anomalies in real time. Think of it as having a guard at the door, constantly monitoring every person who enters, rather than reviewing footage hours later. Online learning, on the other hand, allows the system to adapt and improve on the fly. Unlike traditional machine learning models, which are trained on static datasets, online learning continuously updates itself with each new data point. This is essential in dynamic environments where the nature of anomalies is always evolving, like in cybersecurity, where hackers are constantly developing new attack methods. Of course, like any advanced technology, real-time anomaly detection comes with its challenges. Scalability is a significant hurdle, with the sheer volume of data generated by modern systems ensuring that detection remains fast and efficient without overwhelming computing resources is no small feat. And then there's the issue of false positives. Real-time systems need to strike a delicate balance. If they're too sensitive, they may flood operators with unnecessary alerts, causing fatigue and missed opportunities to catch true threats. If they're not sensitive enough, they risk overlooking critical anomalies that could lead to severe consequences. But despite these challenges, real-time anomaly detection is revolutionizing how we respond to potential threats. It's not just about catching problems, it's about changing the game entirely, creating proactive systems that prevent issues before they escalate. The bottom line? In a world that demands instant action, real-time anomaly detection is the frontline defense for industries that can't afford to wait. It's the key to a safer, faster, and smarter future. And with this foundation in place, let's take a closer look at how real-time anomaly detection is applied in the real world. Because theory is one thing, but the impact in real life is where the magic truly happens. Stay with me as we dive into slide 12 and an incredible case study about credit card fraud detection. Let's dive into the real world and see how anomaly detection is solving one of the most pressing challenges of the digital age: credit card fraud. With millions of transactions occurring every second worldwide, detecting fraudulent activity isn't just important, it's critical. But how do financial institutions sift through mountains of data and identify those rare, malicious patterns? That's where anomaly detection comes in, and it's changing the game. Fraud detection in credit card transactions is like finding a needle in a haystack. Imagine this: a customer regularly spends a few $100s per week on groceries and small purchases. Suddenly, there's a charge for thousands of dollars from another country. A human might not notice this anomaly until the customer files a complaint, but an AI-powered anomaly detection system flags it instantly. Here's how it works. The first step is data collection and pre-processing. Financial institutions pull transaction data from millions of users, including details like the amount, location, and time of each purchase. But raw data is messy, filled with duplicates, missing entries, and inconsistencies. Pre-processing ensures the data is clean, normalized, and ready for analysis. This step is critical because even the most advanced anomaly detection algorithms are only as good as the data they're fed. Once the data is clean, it's time for model selection and implementation. Financial institutions rely on algorithms like Isolation Forest, which excels at identifying rare, distinct behaviors, or Local Outlier Factor, LOF, which focuses on how unusual a transaction is compared to its nearest neighbors. In some cases, autoencoders, a type of neural network, are used to detect subtle, non-obvious anomalies by reconstructing transaction patterns and flagging any significant deviations. The models are trained on labeled datasets, where past fraudulent and legitimate transactions are already known. Cross-validation is then used to fine-tune the models and ensure they perform well on unseen data. But the real magic lies in the results. With anomaly detection systems in place, financial institutions are achieving accuracy rates of up to 95%, with precision levels over 90%. This means fewer false alarms and more real fraud cases caught in real time. And the impact? Enormous. Banks using these systems have reported a 30% reduction in fraud losses within the first year of implementation. That's not just numbers on a balance sheet. It's about protecting customers' trust and ensuring their financial safety in an increasingly digital world. What makes this case study so fascinating is how it highlights the power of anomaly detection to transform a seemingly impossible task into a solvable problem. By combining clean data, advanced algorithms, and real-time processing, financial institutions are staying one step ahead of fraudsters. But credit card fraud isn't the only place where anomaly detection is making waves. In the next slide, we'll look at how this same technology is being used to combat another critical challenge, cybersecurity. Let's explore how anomaly detection is defending networks from invisible threats. Now, let's talk about a battlefield that's growing more dangerous every second: cybersecurity. As organizations rely more on digital infrastructure, the threats to their networks are evolving at an unprecedented pace. Malware, phishing, data breaches, and ransomware, these attacks are becoming more sophisticated, stealthier, and harder to detect. This is where anomaly detection becomes a game changer, helping to identify and stop cyber threats before they cause chaos. Imagine a company's network handling millions of data packets every second. Most of this traffic is routine: emails being sent, files being accessed, and applications running. But then, hidden in the noise, a single IP address starts transferring unusually large amounts of data to an external server in the middle of the night. On the surface, it's easy to miss, but an anomaly detection system flags it instantly. This is no ordinary activity. It's data exfiltration in progress. In network security, anomaly detection begins with data collection. This involves pulling information from firewalls, intrusion detection systems, and network logs. The key is to capture relevant attributes like packet size, source and destination IP addresses, and connection duration. But raw network data is messy. It's filled with noise and irrelevant information. The first challenge is to pre-process this data, filtering out the noise and extracting the features that matter most for detecting unusual activity. Next comes model selection and training. In this case, algorithms like isolation forest are used to handle high-dimensional data, while support vector machines, SVMs, are employed for binary classification of normal versus anomalous traffic. The training process involves using labeled datasets, with 80% of the data used for training and 20% for testing, ensuring the model learns to recognize patterns of both legitimate activity and known threats. Once implemented, these systems deliver powerful results. In one real-world example, a network security anomaly detection system achieved a 95% detection rate for known anomalies, with a false positive rate of just 2%. This balance is critical. Too many false positives can overwhelm security teams, while false negatives can allow devastating attacks to slip through. The impact is profound. With real-time detection, organizations can respond to threats 30% faster, reducing the time it takes to contain and neutralize attacks. Whether it's spotting a brute force login attempt, identifying a rogue device on the network, or catching a malware payload being delivered, anomaly detection systems give organizations the upper hand in a fight that never stops evolving. But network security isn't just about stopping today's threats. It's about preparing for the future. Continuous improvement is key, with models being refined through feedback loops and updated as new data flows in. The emergence of deep learning techniques is further enhancing anomaly detection capabilities, allowing systems to detect more complex, subtle patterns in increasingly vast datasets. Cybersecurity is one of the most critical use cases for anomaly detection, but it's not the only one. Let's look ahead into the future of anomaly detection, because the technology isn't just evolving, it's transforming into something smarter, faster, and even more integrated into our daily lives. As data grows exponentially and systems become increasingly complex, the future of anomaly detection will be shaped by three revolutionary trends: deep learning integration, real-time analytics, and automated machine learning. First, let's talk about deep learning integration. Traditional anomaly detection methods, while effective, often struggle to handle the sheer complexity of modern datasets. Enter deep learning, where neural networks can process and learn from incredibly intricate patterns. These models don't just look for simple outliers, they can identify highly complex relationships within the data that were previously impossible to detect. This means better accuracy, fewer false positives, and the ability to detect anomalies in large, unstructured datasets, such as video streams, images, or real-time IoT data. For example, think about an industrial system with thousands of interconnected sensors. Deep learning models can analyze all of these signals simultaneously, spotting subtle shifts or patterns that traditional algorithms would miss, like a machine behaving just slightly differently before it breaks down. This capability allows for more precise predictions and proactive interventions. Next, there's real-time analytics. As we've discussed, anomaly detection is moving into real-time environments where decisions need to be made in milliseconds. The future of real-time anomaly detection lies in the adoption of edge computing, where AI models run directly on devices like sensors, cameras, and IoT systems, rather than relying on the cloud. This eliminates latency, enabling ultra-fast responses. Imagine self-driving cars equipped with edge AI that detect road hazards as they happen, or energy grids that identify potential blackouts before they occur. Real-time analytics will also drive innovation in areas like smart cities, autonomous systems, and critical infrastructure. By processing data at the source, these systems will become faster, more efficient, and more reliable, fundamentally transforming how we interact with the world. Finally, let's look at automated machine learning, AutoML. Right now, building and tuning anomaly detection models requires expert knowledge, time, and effort. But with AutoML, the process becomes more accessible, even to non-experts. AutoML platforms automate tasks like model selection, hyperparameter tuning, and performance optimization. What does this mean? Faster deployment, broader adoption, and more industries able to leverage the power of anomaly detection without needing a team of data scientists. Automail democratizes AI, allowing businesses, healthcare providers, and even small organizations to implement cutting-edge anomaly detection systems that were previously out of reach. As we move forward, these trends will redefine what anomaly detection can do, pushing it beyond traditional boundaries. From AI that thinks like humans to self-learning models that evolve in real time, the possibilities are endless. The future of anomaly detection is deeply interconnected with the future of AI itself. It's not just about finding anomalies anymore. It's about creating intelligent systems that proactively protect, optimize, and improve the world around us. And with that, we've laid the groundwork for what's ahead. Up next, we'll bring everything together as we conclude with the key takeaways from our journey into anomaly detection. We've reached the end of our journey into the world of anomaly detection. Let's take a moment to step back and reflect on what we've learned, because this isn't just a story about technology. It's about how AI is reshaping industries, saving lives, and protecting the systems that keep our world running. At its core, anomaly detection is about finding what doesn't belong, those rare hidden events that carry outsized importance. Whether it's a fraudulent credit card transaction, a cyber attack, a failing machine, or an early sign of disease, anomalies matter. They're the signals in the noise, and detecting them quickly and accurately can make all the difference. We've explored how techniques like statistical analysis, machine learning, and deep learning are used to identify these anomalies. Each approach has its strengths, from handling simple outliers in structured data to analyzing complex patterns in massive, unstructured datasets. The methods are diverse, but the goal is the same: to uncover what's unusual and act on it before it's too late. We've also seen the incredible applications of anomaly detection across industries. In finance, it's stopping fraud before it drains accounts. In healthcare, it's saving lives by catching medical emergencies early. In cybersecurity, it's the frontline defense against evolving threats. And in industrial systems, it's preventing costly failures and ensuring critical infrastructure keeps running. But the journey isn't without challenges. Implementing effective anomaly detection systems requires tackling issues like data quality, scalability, false positives, and the need for domain expertise. Balancing sensitivity with accuracy is a constant struggle, especially in high-stakes environments where the cost of errors can be enormous. Yet the future of anomaly detection is bright. With advancements in deep learning, real-time analytics, and Automail, we're on the verge of a new era. Anomaly detection systems will become faster, smarter, and more accessible, enabling even small organizations to leverage their power. AI will evolve into self-learning systems that adapt in real time, detecting threats and opportunities we haven't even imagined yet. So, what does this all mean for us? It means we're living in a world where proactive intelligence is no longer a luxury, it's a necessity. From protecting our finances to securing our systems and improving our quality of life, anomaly detection isn't just a tool, it's a foundation for the future. Thank you for joining me on this exploration of anomaly detection. If you found this journey valuable, don't forget to share it. And if you want to stay updated on the latest in AI, machine learning, and cutting-edge technology, make sure to subscribe. The future of AI is happening right now, and it's shaping the world around us in ways we're only beginning to understand. Let's be part of that future together.